Hi everybody, we go to chapter 10 in Calculus 2. In this chapter we study about sequence and series. Right, just some definition. A sequence is an order list. So it is a list of numbers, individual terms are written as a sub 1, a sub 2 and so on. A sequence may be given in the recurrence relation where we have the n plus 1 terms, the n plus 1 n plus first term in the function of a sub 1 and a sub n. So pretty much the next term is defined by the previous terms. It could be more than one. And usually a recursion, we need to know where we start, and then we get from this term to the next, and then from this term to the next. In that way we generate the whole sequence. So if it's the case, it's called the recurrence relation or recursive formula. If we just have a sequence in the explicit form, that means here we have the function for a sub n. It only depends on n, does not depend on the previous term or previous terms. Right, so recurrence relation or recursive formula depends on the previous term, and this one only depends on n. So another way to define sequence is it is a function whose domain is natural numbers. Right. I will write that too. So another definition for sequence. Sequence is a function, so it is like a function like this, whose domain is the set of integers. I should say whole numbers because it might start from 0. Yeah, so we use this definition for something like this. And the initial may start from 1 or may start from 0. Actually, it can start from any negative number, but it cannot be 1.5, something like that. Have to be whole numbers. Could be 0, sometimes even negative still. Anyway, write the first 4 terms of the recurrence relation for the following. The first 4 terms and the recurrence relation. Right, so pretty simple. We have a sub n equal to 1 over 2 to the n. So for 4 different values of n, the first 4, then it works. By the way, by default, sequence starts from 1, unless sometimes it starts from 0, but we have to specify that. But in this case we said the sequence starts from 1, index is 1. So just like make a table, pretty much. Yeah, so if we have n, just n, and here a sub n, 1 over 2 to the n power. Yeah, 1, 2, 3, and 4. So when we put 1 in for n, this n and that n, we have a sub 1 equal 1 over 2 to the first, or 1/2. A2, 1 over 2 to the second, 1/4. A cube, 1 over 2 cube, 1/8. And a to the 4th, a4 is 1, 2 to the 4th power, 1 over 16. That's simple enough. Those are the first 4 terms. Of course, if we draw the graph, it will be like this. Right. By the way, on the calculator, if we want to do this, of course, we can either do a function. In that case, we just say 1 over 2 to the x, and then we go to the table. That works just fine, right? Right. Or we say, we did this on the section 8.8. We just say function we apply to the first 4 terms, right? 1, 2, 3, and 4. You see, and here we can convert them to fraction, and yeah, it's no big deal. The problem is rather simple, right? But we can also put the sequence in the calculator. So hit mode. In the calculator, there are 4 type of graph, function, parametric, polar, and sequence. Corresponding to those 4 modes, we have x, t, theta, and n. So if we want sequence, so that's the sequence mode, and that will be the variable should be n. Right, so highlight the sequence, and then we just say what the sequence look like. It is 1 over 2 to the n power, and then we can hit graph. It will graph the point like we have here. Right, Windows number 6. Sorry. Zoom number 6. Yeah, because it is too small to graph, and that's all we see here. Right. Second table, and it give us the same thing. Right. And convert to fraction, no big deal. Right. So those are first 4 terms. Very easy, but I just want to show you how we use the calculator. Alright, how do we get the recurrent relation? Now let's just write that in terms of sequence like a list. So we have 1/2, 1/4, 1/8, 1/16, and I'll ask you what will be the next term, and you said it will be 1 over 32, right? And it is. So that will be 1 over 32 will be next. So we said we have 1 on the top, and at the bottom we multiply by 2, and that's exactly what we have. Instead, we can say to get from this term to the next, we have to multiply by 1/2. To get from this term to the next. So in that case, what we have is the recurrent relation. Is this. The first term is 1/2. And to get to the next term, we will take this term, multiply by 1/2. So this is the recurrence relation. We start from 1, and then the next term is half of the previous term. Usually when we write this, we should say n greater than or equal to 1. Yeah. So that is the recurrence relation for that explicit formula. Right, simple enough. Right. How do we put? Notice this number, right? Now, we can also put the recurrence relation in a calculator. I'm not going to. Anyway, let's just do that. Now, so we say this term is equal to the half of the previous term. So in the calculator, we have to do a little bit differently. So we say it's going to be u of n instead of a1. So input here is in the form of a function. So if we want to, the calculator should be, instead of that, in calculator will be u sub n equal to u sub n minus 1 multiplied by 1/2. So if we put in the calculator, that's what we have to put. So u sub n is going to be u. First, the u is second number 7. So u of n minus 1 times 1/2, or divided by 2, if we can also like that, type like that. And the first term is 1/2. Yeah, we have to do. And we start with 1, and the sequence at that is equal to 1/2, and that's it. And we have the same sequence: 1/2, 1/4, 1/8, and so on. So that's how we type the recurrence relation. Right, now let's go here. Write the first 4 terms and the explicit formula. So in this case, we are given a recurrence relation. We will write the explicit formula. Right, let's start. So pretty much we just choose the values for n and we substitute in here. We have a1 is 5. That's what given. Easy. The next one, to get to a2, we're going to let n equal to 1, and we substitute into here. 1 plus 1 right? Yeah, put 1 into here, into n here, and so that gives us a2 equal to a1 minus 3. a1 is 5 minus 3 is 2, n equal to 2. We're going to put 2 in for n, so that gives us a 2 plus 1 is 3, and 2 here, so it will be a2 minus 3, and we'll put a2 in there. It's -1, and then n equal to 3. Do the same thing. a4, because 3 plus 1 is 4, and then here's a3 minus 3 minus 1 minus 3 is -4. So we have 5, 2, -1, -4, and it can go further. So we have the explicit formula. How do we write the general formula? Oh, of course, I mean the explicit formula or general formula. Now, for that, I will write this one again. The first term is 5. The next term, 5 minus 3. Instead of write 2, I write 5 minus 3. Now, let's just write the list of numbers first. We have 5, 2, -1, -4, and so on. We see the pattern clearly, right? So, from this term to the next, we will -3. That's the recurrence relation state. So it's the previous term -3. And then to get to the next one, we -3. And then so on. So if this pattern develops, to get to a3, we're going to have 5. And we will have 2 of the -3. Right? And then a4, how many of -3? 1, 2, 3. 3 of the -3. And if this pattern develops, when we go to a sub n, it's going to be start with 5, and we're going to have n minus 1 times 3. So think about that. The second term, 1 step. The third term, 2 steps. the fourth term 3 steps. So it's always take start from the first one, it will take one less step to go to that particular term. So if we want to go to a sub n, it's going to be n minus 1 step, and each step is the minus 3. So this is a general formula. Right. Now, definition. Now, if the terms, now we just get to a little calculus here. All of that is just coarse algebra, pretty much. Now, if a term of sequence approaches to a unique number L as n increases, that is, if a sub n can make arbitrarily close to L by taking n sufficiently large, then we say the limit as n goes to infinity equal to L. And if there's such L exists, then we say the sequence converges. So this is conversion. And this is exactly the definition of the limit. If the limit here does not exist, that is diverges, where the no limit will be divergent. Right. So, and the way we define this limit. So usually when we say the limit of a sequence, we mean when n goes to infinity, because the sequence is unlike function. It could go from negative infinity to infinity. This one we start from one term, the first term, that's the first term, and then the term when n goes to infinity. So it's only approaching the limit only on one side. Right. Now let's find the limit for this sequence. Write the first 4 terms of each sequence and discuss the limit of the sequence. Alright, so now we just write, put n in. Okay, the way we do this, first 4 term, right? Here we have the explicit formula. Usually we better alpha y equal to, I want to type exactly like the way we see it. And then n squared plus 1. Right. Now we will hit alpha trace y1. No, we cannot do that. What was this? That is u, right? So u is second, number 7, and we want the first 4 terms. So curly bracket 1, 2, 3, and 4. Close curly bracket and close. We could put this in the list 1 and evaluate at list 1 like we did in section 8.8. We have that. How about fraction form? There it goes. So the first 4 term. So this is the way we write the sequence in the curly bracket, because the sequence is the list of numbers. So we write that as a set of numbers. So we say it negative 1/2, 1/5, negative 1/10, and 1/17. And then that's the first 4 term, and then just keep on going. Right. In the next section we will have the notation for the sequence, but for now we just see that we see at the bottom the top, it could be negative, positive, it doesn't matter. In fact, it's just alternating from positive to negative, positive, negative. But what we focus on is at the bottom though. It will get bigger and bigger, right? As n increases, the denominator goes to infinity, and in that case the finite number on the top, positive, negative, doesn't matter. The bottom goes to infinity, therefore the whole thing So I just say if this continue, we're going to have either plus or minus 1 on the top, doesn't really matter, but the bottom goes to infinity. So we have a finite divided by infinity, so that will go to 0. So the limit of the sequence go to 0. Also we write limit, may not be right the notation for that. I'll just write the limit for a term. Right. Yeah. By the way, we'll just find this limit just like the limit of a function, but we'll do more of that in the next section. Right, next, cosine of n pi. Is this in radian mode? Yes. Cosine of n pi. Right? And the nice thing about this is we already type this in. Right? So we evaluate the sequence for the first 4 terms. And we evaluate. So that is negative 1, 1, negative 1, and 1. If this pattern continue, it's just alternating between negative 1 and 1. In that case, we say the limit does not exist because this pattern does not approach into any number. So we say the limit does not exist. It's not equal to, just does not exist. And if the sequence does not exist, we say that, if the limit does not exist, we say the sequence diverges. Next, we have this sequence. A sub n plus 1 equal negative 2, a sub n when n equal to 1. So that is the recurrence relation. We start with the first n, let's say n equal to 1. We start with 1. And then we have negative 2, a sub n. That means u sub n minus 1. Yeah, so that is the equivalent to that. This here. And initially we start with 1. Right? And the same thing here. Evaluate the function for the first 4 terms. That's what we have. Or we just do it by hand. N equal to 1. A1 is 1. N equal to 2. Sorry, that is a terrible way to write it. We start with A1 equal to 1. There's a typo, no wonder I was confused. Sorry, this should be 1. Right. So we start with A1 equal to 1. When n equal to 1, we're going to put 1 here. That gives us 1 plus 1, A2 equal to negative 2 times A. And when we put 1 in for n, we have A1. So negative 2 times 1, n equal to 2. Put 2 in here. 2 plus 1 is 3. And we have 2. Put 2 in for n. That A2. And that 4. N equal to 3. A4. Negative 2. And we're going to put 3 in here. That 4 and 3 here. That A3, and which is 4, and negative 8. So we have 1, negative 2, 4, negative 8. So we say h of n, if we want to n from 1 to infinity, equal to 1, negative 2, 4, negative 8. And if this pattern continue, the number will get, I'm not saying get bigger or smaller, but the magnitude will get bigger. The sign will alternating from positive to negative, but the number will get bigger and bigger. So in that case, the limit does not exist and the sequence diverges. Next, find the limit of this sequence. Now that should be fairly simple. All we do is just find out the limit of the function. As n goes to infinity, now we say put n in here, we have infinity over infinity. So that is the Hospital rule. Take derivative at the top, derivative at the bottom. But that sounds like a lot of work, and this is a lot of work. So what we focus here is just later on, this will be extremely helpful. When we have a bunch of terms, just take the term with the highest power. In this case, so because n is significantly bigger than 1 when n go to infinity, so infinity plus 1 not really doing much, right? So in this case, we just take a 1 with a higher power, highest power on top, highest power at the bottom. There will be a more general statement, but here we say as n goes to infinity, the polynomial, the one with the highest power matters. Only the term with highest power matters. We'll extend this into something more general in the next section. So in that case, I will take this term on top, this term at the bottom. And the n cube cancel out. And we just have 4. There's no place to put in the n, so we just say that is 4. So we say the sequence is convergent, and the limit of the sequence is 4. Simple enough. So that is just brief introduction of a sequence. So sequence is the list of a bunch of terms. Two ways to define that: recursive formula, or recurrence relation, or the explicit formula. Then we can find the limit. By limit, we mean when n goes to infinity. Right. Next, we go to the series. So the difference between the sequence and series is sequence is a list of numbers, so they have individual terms, whereas series is a sum. So that's the most important. In the series, by the way, when we talk about series without any reference, we refer that to be infinite series. So when we just say series, we mean infinite series. right? Given a set of numbers and the sum, so that's important. A series is a sum, and it's called an infinite series. So it go from 1 to infinity. That's why I call the infinite series. Right now, is sequence of partial sum. So partial sum, of course, is not an infinite sum. It will stop at n. So s1 we stop at n equal to 1. Stop at n equal to 2, we have s2, and s of n we stop at s at a sub n. So we still add all of them up to when n equal to that particular case, right? So we're just adding from the first term to the second until whatever this index indicate. If the sequence of the partial sum has a limit, then we say the infinite series converges to that limit. Excuse me. So we say the sum, this is infinite sum, the partial sum that 1 go to n, and we take that n goes to infinity, and if L exists, we say it is convergent. If L is not, we say it is divergent. So the limit of a sequence when the term goes to infinity, the limit of a series when the sum goes to some number when n goes to infinity, right? So a sequence, limit of sequence is the limit of just one term when n goes to infinity. The limit of a series is the limit of a sum when n goes to infinity. So when we have the whole thing like that goes to infinity. Right. Let's look at this example. Consider this infinite series 1/2 plus 1/4 plus 1/8. Right. So we have a sketch here. So originally we have 1/2, half of a square. That makes sense. Next, 1/2 plus 1/4. So we have half of a square. Now add a quarter to it. So we have that. Now, then half of the next one, then half of the next one, and then just keep on. So, of course, when we just keep doing that, essentially, we're going to have the thing that is left over is extremely small. And we just cut in half and half and half of whatever left. And essentially, if we keep doing that, it is equal to 1. And this is actually a very common kind of a paradox. So instead of using the square, there's another way to visualize this. Is I'm going to draw this. So let's say we have an arrow, bow and arrow, and from here, and we shoot to the target here. Originally, the arrow traveled half of the distance, and then half of the remaining, and we just have half of the remaining distance, and we just keep doing that. Essentially, the arrow will hit the target, right? By the way, this is part of what we call the Zeno paradox. Not exactly, but it says that Zeno paradox is dealing with different things, but the concept is kind of similar. If we just keep getting half and half, and then Zeno say, doesn't matter how close the arrow to the target, we can always cut that in half. And he reasoned that if that just keep developed, doesn't matter how small that number is, we will never hit. The arrow will never hit the target because the distance doesn't matter how small, we can always divide by 2. But of course we know it's not true, right? If this one hit, that distance just gets smaller and smaller. But if you add all of them up, essentially it is equal to 1. So if this one goes to infinity, this is equal to 1. However, if this one goes to any finite number and not infinity, that is very close to 1, but it's not going to be 1. It is 1 only when it goes to infinity. Next, we have this sequence, 0.9 plus 0.09 and then so on. And of course, if we do that, if we write that out, it's like 0.9999, and of course, essentially it goes to 1 as well. But let's just write. I'll find the partial sum of S1. S1 meaning we have one of the term. S2, the sum of the first two terms. S3, the sum of the first three terms. And infinite series, as this keep going, we will have this number repeating decimal of 0.99999, and essentially, of course, when this one goes to infinity, that goes to, or we can say it, this partial sum goes to 1. Right, and this one, so that's actually very simple. This one, consider the infinite series of that. For the first 4 terms, the partial sum. I will use the calculator here. Right, notice this is the first 4 terms of the sequence of the partial sum. So we are not finding the first 4 terms of the sequence. We find the first 4 terms of the sum. That means we're going to find S1, S2, S3, and S4. Right, but we still enter the sequence like we said. 1 over k and k plus 1. I use n instead of k. Right. Now if we want to, we can use the summation that we did before, but it's going to be math. It's not, this is sum, it's just add everything in the sequence, so we're not going to use that. We use the summation notation. Math, let's clear everything. Math, option 0, summation. And now with the first 4 terms, so we start from 1 to 1, and then we just have use of n. So the first one is 1/2. Right? By the way, and then if we want to, let's just do that again. This time we go to 2, and that is 2/3. Right, let's just write the sequence first. So this is the sequence, not the series, sequence. So sequence of the first 4 terms, 1, 2, 3, and 4, close. Convert to fraction. Right. So in terms of sequence, individual terms is 1/2, 1/6, 1/12, 1/30, 20, sorry. So this is 2 times 1, 2 times 3, 3 times 4, 4 times 5, and so on. Now into a sum. or the partial sum. S1 is just the first term. S2, the sum of the first two terms. That 2/3. Yeah, that 2/3. Now if we go to 3, sum of the first three terms. Right? So sum of the first three terms. And S4, sum of the first four terms. So the partial sums. What do you think that will be? Four-fifths. Now, let's look at the sequence of the partial sum. So this is called the sequence of the partial sum. Now let's write out the sequence of partial sums. We start with 1/2, 2/3, 3/4, 4/5. If I ask you what is the next number, you'll say that easy, right? 1, 2, 3, 4. So the next one is 5/6. So if this pattern continue, we're going to have first term, second, so it will be n over n plus 1. Right? So the first term is 1/2. So the bottom always weighs 1 more than the top. And so pretty much that. And it said what make the conjecture about the values of the series. We said the values of the series, we mean the values of the infinite series. So we say limit of s of n as n goes to infinity is the limit of n over n plus 1. And just like the previous example, we'll take the one with the highest power. Because n goes to infinity, plus 1 really doesn't do much with the plus 1. Or we still say, in chemistry or physics, we just say the plus 1 here is negligible. That cancels out is 1. So we say the values of the series is equal to 1. Or we say the limit of the partial sum is 1 as n goes to infinity. Right. That's pretty much the section, but we just want to write into the summary in terms of the notation and other things. So in here we have the independent variables. In sequence series is n. So usually we don't call that even a variable. We call those indexed. N here we call that index. Dependent variable is the function we write like that. A sequence we write like that. And the domain is integers. Actually, like I said, it could be negative, but without anything specified, we will say the first term is n equal to 1, and then so on. But in function, it could be any set of real numbers. It could be 1.5 and anything in function. We have the sum and the integral. So just the integral, meaning it will continuously from 1 to n. This one will go from 1 to n, but only integer values. Right. We're going to study more of this, but That's it for the section 10.1. See you in another video in Calculus 2. As always, thank you for watching.